Now that we have our definition of continuity, we are going to talk about continuous functions. A continuous function is a function that is continuous at every point in its domain. So as we look at this function y equal 1 over x, we see that there is a point of discontinuity at x equals 0, but if we're asking what is the domain of this function, the domain of this function is everything except x equals 0. So we have from negative infinity to 0, 0 to infinity. We're leaving out 0. So this function, as far as talking about what a continuous function is, this is a continuous function. There's a point of discontinuity at 0, but 0 is not in the domain of the function. So the function itself, for all values of the function, is continuous. We have a theorem, and the proof of this theorem, there is a link to the proof of this theorem following this video. And it says, if f is continuous at b, and the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x equals f of b. So as we look at this, essentially what this is telling us is if we have the limit of f of g of x, that would equal f of b, but b equals the limit as x approaches a of g of x. And so if we substituted that in for the b, we would have f of the limit. So I think you could see that since b equals this, we could take this and substitute it here, and that's essentially what we're saying here in other words. But what that is telling us is when we have this kind of composition, we have one function inside of another, and we need the limit, we can actually compute the limit of the inside function first and then apply the outside function. So the order of the function evaluation and a limit may be reversed. Now this will only be true for continuous functions. We don't know, and most of the time it will not be true if the functions aren't continuous. So that is one of the important requirements, is we have to have continuity for this to be true. But if this is true, we can reverse that order. And here's an example where this may be useful. If we want the limit as x approaches 4, we first have the square root function, and then inside of that we have the function x squared plus 9. F and g are both continuous at x equal 4, and so we can take the limit inside of the square root function and go ahead and work this inside function, and we can do that with direct substitution since we have this continuous function. So we can substitute in 4 squared 16 plus 9 is 25, and then we can apply the outer function, which is the square root function, and get 5. So that's something that can be important to us. The function evaluation and the limit can be reversed as long as we have continuous functions. Let's look at another theorem, and we will see the proof of this one, the continuity of composite functions at a point. If g is continuous at a and f is continuous at g of a, then the composite function f composition g is continuous at a. Now, if we wanted to prove that this was true, remember the definition of continuity, we would need to show that the limit as x approaches a of the composition f of g of x equals f of g of a, because the function value needs to be defined and it needs to equal the limit at that point. So if we can prove this statement here, we have proven that the composite function is continuous at a. Well, let's look at that left-hand side, the limit as x approaches a of f of g of x. Because we know that g is continuous at a, we could replace the g of x with g of a. We could directly evaluate this with the limit, so we'd have f of g of a. And that is the limit as x approaches a of g of x. And with the theorem that we just had, where we can have this limit inside or outside, we can do the function evaluation and the limit in either order. Then we have shown here that f of g of a equals the limit as x approaches a of f of g of x. Now, if we have f and g continuous at a, could we determine if the following functions were continuous? What if we added the functions, subtracted the functions, multiplied the functions by a constant, took the product of the functions, the quotient, or take the function to the nth power? And Hopefully you remember the limit laws, and this should be obvious to you because to have continuity, the function value at a needs to equal the limit at a, and we had our limit laws that essentially tell us that if we have the limit as x approaches a of a sum, that equals the sum of the limits. And so it would be very easy to prove. I'm going to just do it for part A, and then you could see that we could prove it for all of these others using those limit laws, and the only one that would have a restriction on it would be E, where of course we would need to say that the denominator could not equal 0. So let's look to prove this for just part A, and then we could see that the rest would be analogous. So we would have the limit as x approaches a of f plus g of x, and we know by the limit laws that that's the limit as x approaches a of f of x plus the limit as x approaches a of g of x. But because we know f is continuous at a, then we know this limit equals the function value, so that equals f at a, plus because g is continuous at a, we also know that the limit as x approaches a of g of x equals g of a. And then having these two functions summed together by the properties we learned in college algebra, this equals f plus g at a. So essentially we just showed that the limit equals the function value at a, and therefore this sum of two functions is continuous. The others could be proved very similarly. So polynomial and rational functions, we're going to look at if those functions are continuous, and remember the definition: a function is continuous if it's continuous for each point in its domain. And we know for polynomial functions that the domain is all real numbers, so this should be easy to see that polynomials are continuous functions. And rational functions, because the numerators and denominators are polynomials, would be continuous functions except at that point of discontinuity anywhere the denominator would equal 0. So it's continuous for all x for which the denominator is not 0. So let's look at some of the transcendental functions. Let's look at the trig functions. Of course, sine is easy to see. We've got continuity. If we just looked at the graph and we picked any point A, we can see that the limit as we approach A is the same as the function value at A. Sine is a continuous function. Cosine would be the same because they look very similar, just phase shifted by pi over 2. But what about tangent? As we think about tangent, is tangent a continuous function? Well, we have all these points of discontinuity where these vertical asymptotes are, because we know tangent is sine over cosine, and anywhere cosine would equal 0, we would have a point of discontinuity. But those vertical asymptotes, or those points of discontinuity, are actually excluded from the domain. So tangent is a continuous function since it's continuous for all points in its domain. That will be the same will be true for the other trig functions for the very same reason. The points of discontinuity, the vertical asymptotes for these particular trig functions, are excluded from the domain. So these are considered continuous functions because they are continuous at every point in their domain. So, summarizing, the following functions are continuous at every point, and that's the important part, in their domain. So polynomials, rational functions, because the values that would make the denominator 0 are excluded from their domain. Root functions, trig functions, inverse trig functions, exponential log functions. Oh, I don't know why that ran across the top here, but we're going to look at the intermediate value theorem. The proof of this theorem is a little deeper than the tools we have, so it's typically not proven until more advanced math texts. But it's an important theorem to understand what it says, and the idea is not hard to get an intuitive feel for why it would be true. Suppose that f is continuous on the closed interval from a to b, and let n be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c on the open interval somewhere between a and b, such that the function value at c equals n. This intermediate value theorem will be used various times as we develop other ideas in calculus, and so it's important to understand it. It's probably best understood looking at a graph. Okay, looking in the upper left graph, we basically have a situation where we're going to be looking on the interval from A to B, and we have a continuous function there. So here is our continuous function. If we choose some value n that is between f of a and f of b, and f of a cannot equal f of b, and so n is somewhere between. So here's our f of a and here's our f of b and here is our n. What the intermediate value theorem says is somewhere between a and b there is a value c such that when you compute the function at c, that equals n. It's called the intermediate value theorem because if you have a function that is continuous and you're looking at f of a and then f of b, this function, because it is continuous, must take on all values between f of a and f of b. So you can choose some arbitrary n between f of a and f of b, and there will be some value between a and b. When you compute the function at that value, it does equal this value n that's in between f of a and f of b. Now this bottom figure essentially is showing us it could happen more than once. The intermediate value theorem just guarantees that it happens. So this is showing us as we look on the interval from a to b, and we have a continuous function there, and we're looking at f of a and f of b, and then we choose a value n between f of a and f of b. So here is our n. Somewhere between a and b there exists an x such that the function at this value will equal n. And in this particular illustration, it shows you there's actually three of those. F of c1 equals n. You can see here f of c2 also equals n, and f of c3 also equals n. So it could happen more than once, but guaranteed to happen at least once. So here's a little kind of cartoon, but basically helps us understand or see why this theorem would be true. Why did the chicken cross the road? Because he wanted to get to a point on the other side, and the only way to get to a point on the other side, because he has to have a continuous path, is he has to cross this value n, which is where the road is at some point. So the only way he can get from f of a right here to f of b right here is to go across this value n.